My name is Atsuki Shiga from YMG Japan, and I will be presenting about development and application of cement ramps, porous concrete, granite concrete. Currently in Japan, the depletion of natural resources such as aggregate and natural freshwater used as raw materials for concrete is becoming an issue, and the importance of effective use of resources is increasing. From this viewpoint, there is a growing movement in Japan to effectively utilize concrete returned from construction sites and byproducts generated from other industries as materials for concrete. In this context, Nagoku ready-mix concrete in Japan has applied granulation technology to return concrete and developed a technology to be used as porous concrete. Therefore, taking a hint from this, we developed a granite concrete and all-west cementless porous concrete using slag-based materials from the viewpoint of effective use of resources and try to apply it in real pavement. Ground concrete is an application for granulated cement porous concrete, which is also made of these materials. The material is made by adding and mixing a fluctuating agent and a rapid curing agent to the base concrete, which causes the mortar and cement content to laminate and attach around the aggregate. By applying the required compaction pressure, etc., the concrete has the same functionality as porous concrete after curing. This is about the use of granulation technology and the benefit of using it as porous concrete. Porous concrete has many voids inside, and this void provide it with a variety of advantages. For example, the water retention is also useful for controlling the heat island effect. In our experiment using granulated porous concrete, the simulated return concrete, it was confirmed that the water holding time was longer than that of PLC made with number 6 crush stone. And in the case of our PLC, cement flow and compaction strengths are just optimized the bond condition. The following binary image of each cross-section of normal PLC and granulated porous concrete show that the voids are unbalanced in the upper layers. It also shows that the PLC-specific problem of cement paste dropping does not occur with granulated porous concrete. In this experiment, 11 types of mixture were studied, focusing on calcium content, which is important in the curing mechanism of zero cement concrete, and fire rate ratio, which is important granulation, measuring complex strengths after the visual water permeability target areas where no strength is required from grass control measures or simple pavement. Compressive strength was measured at 7 days of materials age after air curing in constant room temperature of 20 degrees and relative humidity of 60%, on the assumption that the pavement would be open after paving. The mixture determined by the experiment is shown here. The compressed strength of this mixture is 1.95 megapascal, which is very low compared to ordinary concrete. However, the actual paved concrete is expected to have higher strength than the experimental value, since people with the right vehicle can pass through the concrete the day after it is placed. Next verification test was conducted for application to pavement. The materials used are not always available at ready-mix concrete plants, making it difficult to use plant mixers. Therefore, a data truck which can be used in existing facilities were used to manual and premix materials and make base concrete prior to granulation. Mixing performance of the base concrete after mixing was very different due to the difference in mixing performance between the laboratory mix and the agent truck. So 50 kg of unit water was added. Thereafter, granulation was done and casted. The casting was completed using simple methods such as temper and load without the use of specific machinery, confirming the good quality of the construction. However, efficiency, improving and materials bias at the concert. Therefore, we aim to reduce materials bias while increasing efficiency by using a larger container and using a plant hopper to input materials while allowing the material to be pre-mixing to some extent. The mixing process reflected 50 kilogram of water volume that was increased in the verification test. The production procedure consisted of feeding the premix materials followed by high-speed agitator for 2 minutes, adding seawater and high-speed agitator for 2 minutes, followed by feeding the flocculant and rapid curing agent. Complex strings tests were performed on the product concrete. The results showed higher results compared to the laboratory tests, and the difference before and after the granulation was about 1/4. However, the fact that on the next day the material could be working on and at the same time the permeability was confirmed suggests results were not affected by the low measured value. In conclusion, taking a hint from granulation technology, an effective method of using return concrete was developed and applied to ground concrete, a new form of cementless porous concrete that uses waste materials. Complex strength tests are conducted, and the results show in greater strength compared to ordinary. However, it is possible to ride up from the next day at the actual site, and it is expected that the difference can be reduced by taking into consideration the retraining effect and other factors. Two verification tests, we were able to find a useful method and it's in line with the current supply chain, and the durability of ground concrete after curing suggests its potential for wide use. In the future, we plan to conduct additional study of test methods and mixtures, as well as evaluation tests and permeability tests. Thank you, Yokai.